This is a good point to give you a little bit of insight into why this conference even happens and why we're starting out with electronic fundamentals. If you look at the schedule going forward, the surveys build upon each other to give you a much more advanced base to move forward with. And so the first base is electronic fundamentals. And Rick Waldron and I did a training session sort of thing up in New York City, and that started this sort of idea of making robots more accessible. Because we did a survey, and I'd like to do that before we get into this, of how many people think if they short this, they're going to erupt in flames. Actually, this is pretty good. Awesome. Most people said that 9-volt batteries will cause them to erupt in flames, and they were all scared, and it was just crazy. If you get a chance and find a 9-volt battery and have never done it in your life, put your tongue to each of the terminals. It's fantastic. That wonderful taste is just electrons flowing through your body. So, without further ado, I'm going to turn it over to our electronics fundamental and making sure it all works.
Thank you, Chris. So I said before, my name is Francis Gulotta. I'm a developer, but I was an electrical engineer in a past life. Not in the way Raquel was a roboticist, like an honest to God, I believe worked for NASA roboticist. Sorry to pull you up. But I did study electrical engineering for a while, and I geeked the hell out about it. So I want to show all of you kind of a brief overview of the things you need to know what's going on. I think it will help you in whatever you end up making today, whatever you end up doing, even if you just want to stay code the entire time. It really, really helps you to know where the electrons go. And so it's my favorite quote from Carl Sagan, and it's also a really, really scary one to see in a workshop. But I promise we're not going to make a universe. We're just going to, learn some theory. So, and I feel like I should give the carrot. What this will get you, like knowing this theory, is you'll be able to take any one of these parts, any LED, any light, any sensor, and you'll be able to know how to power it, how to hook it up, what the schematics mean, or at least what it wants or how it says it should talk and that kind of stuff. And I think that will get, most people really far. And before I start, can I get a show of hands, just sort of a litmus? Who knows what Ohm's law is? Oh, that's amazing. That's beautiful. You guys are going to be bored. All right. The name of this tube I'm forgetting, but it's the basis behind televisions. It's a cathode ray tube, but the experiment had another name. 5 points and a sticker for whoever guesses it or looks on Wikipedia. But it's just a large electrical potential, and they put some phosphorus on it, and it lights up when the electrons hit it, and it's really cool. And this is what's going on in there. And so if you guys remember from physics, electrons are negatively charged, and they like to spread out. They just want everything to be negatively charged, or at least they want it to be as negatively charged as they are. And so if we have an area where there are a lot of electrons, and we have an area where there's not, they will go. So that flow, that movement of electrons is what makes these lights turn on and these computers power up. And it's called current, and is literally the number of electrons moving through a conductor per second, and that gets you amps. I believe it's 1 coulomb, which is an amazing unit. It's like a really large number of electrons, but it's 1 coulomb per second going through a wire. And the attraction, the difference between the highly charged and negatively charged and the low charge, the positive side, that's the voltage. And it's all kind of relative, which is important to know. And also, if it's a lot of difference, then it will move a lot faster. And so you get more current when there's more voltage. So in all your documents, in all everything in the kit should have a data sheet. A lot of these things mean the same thing. So VCC is, I believe it refers to voltage from a power supply. VN is just the input voltage to a thing. If it says +5, it means there are 5 volts coming out of it. in comparison to its ground, the GND, or its 0 volts. And you always have to compare. It's always from a highly charged to a low charged. So this is just so you've heard these terms, and so when you read them later today and tomorrow, you don't go, oh, I don't know what that is, and I'm going to go ask for help. It's good to well, you should ask for help. I don't want to say not, but it's good to just know that it's just saying voltage is in, voltage is out, and what ground is. Make sense? People with me so far? All right, good. Raise hands. Shave. Yeah, okay, cool. All right. So the electrons are great, and I mentioned they flow through a conductor. We call them wires. There's all sorts of conductors. What conductors do is they let the electrons flow through them. I believe there's an exchange going on all the time where they move from molecule to molecule, but you could think of it as sort of like pouring water through a pipe. Some of them are better than others, and we measure this ability to move electrons and resistance. And even humans can be conductors. That's what happens when you lick the battery, which I totally recommend. I have a couple 9 volts if you need. And so we have our own resistance, and even in the Arduinos in your kit right now, they can actually pick up on that. So and I always love it when people decide to use people for sensors, and humans and stuff. The resistors you'll commonly be working with today look like this. The wire, well, all wires have a little bit, but we tend to ignore them when we're working at resistance, because in comparison to the rest of the stuff we're using, it doesn't matter too much. Only when you get really long cables or you're really sensitive, stuff, it doesn't matter. We measure them in ohms, which is a wonderful unit. Coulombs and ohms have nothing to do with each other per se, but I just like saying them. And so all their purpose is to slow down the current flow. In slowing down the current flow, they can heat up, they can light up, they can do all sorts of stuff. And it's one way we let electricity do work for us. I asked about Ohm's law, and since you guys already know this, I'm just going to skip it. It's a very simple equation, but this is the ratio. We had the voltage equals how much current times how much resistance, and we could turn it around. So we want to know how much current's going to flow through something, how much voltage is there, divided by how much resistance. And in the units of volts and ohms, and they just very, very wonderfully fit together. Einstein was quoted, and I don't actually remember the quote, but he loved how perfect physics sort of fit together, and he saw this as evidence of God. I don't know what it's evidence of, but it makes life so much easier. Other resistors are the rheostats and the potentiometers, or pots as we call them. You can adjust rheostats and pots. Pots are great because they're like dials, so you can put big dials on them and be like mad scientist about it. Rheostats are sliders. I've also seen them where they have a tiny little screw you turn. They're maybe in the kits. You may see them today. They're useful for when you need to tune stuff and adjust it. You'll definitely see them with sonar and a couple other things. Symbols, we use diagrams. In fact, diagrams, you'll find a little diagram for every part you pick up, and they look like all sorts of crazy stuff. There are different standards. The United States, the Brits have a standard, the European Union's got one. But basically, it shows how the wires connect. When these are all voltage stuff, ground is usually tied to 0 volts, right? So when you have a battery, you have the positive and negative, and they normally put the negative to ground, and so this is the reference that you can get all the other voltages off of. I'm getting some lost faces. So it makes sense. So when you since voltage is the difference between 2 points, ground is this common point within your project. We could say within the earth, but that's not actually true. That we can reference what the voltage is across. And so if we have a battery and we put one end to ground, then whatever's connected to ground will have the same voltage that from the plus and from the positive side of the battery. I'll come back to that if there are questions. The terms are sort of helpful. I mentioned we had I mentioned VCC and all the other terms for voltage. That helps. Diodes look like that. Diodes sometimes also look like these. There are light-emitting diodes, which are known as LEDs, LEDs. But diodes don't actually have to light up, and they do the same thing, and you'll learn why you might want them a little later. But capacitors, resistors. I'm not going to touch on AC very much, and none of our electronics really work on AC. But AC is basically just, instead of a constant like 5 volts, it's just changing up and down, +5, -5, or like our wall is +110, -110. Swooping back and forth. And electricity, when you start shoving it back and forth, does some really weird things that it's like a whole nother branch of science, of electrical theory, around it, because it acts weird and cool, actually. Some more about LEDs. They've got this special property where they drop a voltage. So without resistance, you just lose voltage when you put when you have electricity flowing through an LED. You need to sort of calculate how much whenever you power up one of these things, you need to control how much current's going through. And so if we take our Ohm's law at the bottom, the voltage across it is always steady. And so you need the rest of the voltage, it goes across whatever resistor you have next to it. Or if you don't have one, the wire, or maybe the inside of your Arduino. So we always pair these up with a resistor. And so part of the voltage, usually about 1.2 volts, drops over the LED, and the rest will drop over the resistor. And so you can then control how much current goes by controlling the value of the resistor. So in this case, I want to use a 190 ohm resistor when I hook 5 volts up to it, so I can get 20 milliamps, and that will make this thing really bright. So whenever you hook up LEDs to any power source, make sure you have that resistor, because otherwise then the current will go much higher. You'll find out what happens. And raise your hands. Who's ever blown out an LED? Who's ever blown it out in an explosive way? Yeah. The rest of you aren't trying hard enough. If you ever use a bench power supply, there are big dials that you can turn to bring the voltage up and down. Those are dangerous around children, so just make sure they're wearing safety glasses. Another component you guys are going to be using today are servos. I didn't write a whole lot about them. You're going to see some really cool demos about them a little bit later, but you can control how the angle of it turns. And most servos that we're going to use today, and I say most because there's a million different kinds, and I'm not precisely sure what's here, will take 5 volts, and we'll take a ground, the 0 volts, and that will power it up. And then you give it a pulse width signal on that yellow, and that controls how that pulse width, which I'll tell you about in a second, controls what angle it turns to. So you can say, I want you to turn like this or that, or maybe I want to lower the paintbrush or lift the paintbrush. And it's better than a motor, which just turns to no end. So just throwing some terms in here. Pulse width. Something you'll see, it's the analog output on your Arduinos. Pulse width literally goes from 0 to 5 volts and keeps changing it. And the percentage of time that it stays at 5 volts versus 0 volts determines the actual width. The width is measured in milliseconds sometimes. Duty cycle is a lot easier to sort of conceptualize. Time's passing. And so half the time we're staying up, half the time we're staying down. The actual width could be, could be like it's 1 millisecond down, 1 millisecond up. But it's the, how do you put it? It's the ratio that matters. And so that's what it is here. This makes sense? Show of hands, wave them if you like them. No, only a little. So the higher the pulse, so in the event of the servo, the higher the pulse, the higher the larger the duty cycle, the more time the servo will spend more time towards the bottom of its range. The lower the pulse, the smaller the pulse, it will spend more time at its top. If you had an LED, it controls the brightness. More time at a higher voltage will give you, a brighter light than a dimmer light. So I keep saying 5 volts, and there wasn't a good reason for me to say 5 volts, but it's actually a standard. The standard's called TTL. There's actually a 3 volt version of it and a 5 volt version of it. Most of the equipment we have, they're 5 volts. Some stuff is 3 volts. Some stuff is doesn't care and will detect, and a 0 and a 1, it doesn't matter if it's a 0 or 3 or 5 volts. Other stuff will fry if you give it the wrong one. So read the data sheets on them. If it doesn't, it will warn you if it's going to die. But if it doesn't say, it's probably 5. But I sort of skipped the important part. When you have, who here has worked with an Arduino? Okay, so that's most people. Arduinos, they have digital output pins, and you can say, I would like to make it, I'd like to write the value 1 or high to the pin, or I'd like to write the value 0 or low to the pin. And that changes the pin's voltage from 5 volts to 0 volts. And that's it. You might be working with some chips today. We call them dip chips. It means there's 2 pins in a row. That's dual inline pin. They are the standard package and the stereotypical chip we've seen everywhere for everything. The only things you really need to know about them is the pins are numbered, and you'll get a data sheet that says what each pin does, and you count them counterclockwise. This one is my favorite chip. You can make it like pulse out however you like, but this is its pin out. You'd hook up, VCC is where you'd hook up the +5. Ground is where you'd put the 0. And then you hook up the rest, however you want to use this chip, you'd hook up to the other pins. But then that will power it up and it will do the right thing. Definitely read the data sheets. If it's not in the box, the chips will say a little thing on it. Google for that number, and there are many websites devoted to just publishing data sheets. Rules of thumb. If you touch it and it's too hot and it burns you, you're doing something wrong, unplug it. That will help you keep the magic smoke in there. And if you do it quick enough, it won't break it. Thank you, everyone.
All right, thank you very much.